Hi, in this video we will see what factors and constants do to a sinusoidal graph. Many of you have already dealt with this in class, but this gives you a full summary of what happens when you manipulate a graph with some constants and factors. And so the equations that we'll look at, y equals a times, and there should be a times in here, sine of x. And then y equals sine of b times x, y equals sine of x minus c, y equals sine of x plus d, and then putting it all together. Now these are two different forms that you'll see. This one I say is nested parentheses, and we use this mainly for writing equations given a picture or given some information. So we'll use this for some modeling. This one here, however, is what you'll see and you'll be given a lot of times. And so that's the one that we'll eventually talk about and how to find the period and phase shift and different things from that. Okay, you should be familiar with some of this language too, but we'll get into this. So first of all, we want to look at a times the sine of x. And so a, well, what happens if I'm going to multiply? You know that the sine of x, the range is from -1 to 1. So if I take a number and multiply it by it, then I'm going to go from negative that value to positive that value. And that's exactly what happens. So if I take a equal to 3, with a equal to 3, 3 times 1 gives me 3. 3 times -1 gives me -3. So what happens with our range is that it gets extended with this a value. Now obviously a might be a half, and so you're not going as high, but what the a does then is it changes what we call our amplitude. Amplitude is 1/2 the max minus the min. So in other words, it's this distance from the center axis up to the top, this distance to the bottom. It's not the full distance. Okay, obviously this is 3, this goes up to 3, down to -3, and so the full distance is 6, but the amplitude we say is only 1/2 of that. Okay, so we can manipulate this. There's 4, 5, and then we can even go negative. What happens when we go negative for our leading coefficient? Well, the amplitude becomes the absolute value of this. And so I'd still go up to 2 and go down to 2. But what happens is that my sine curve has been reflected over the x-axis. And so it starts by going down rather than up. All right, then in summary, y equals a times sine of x. A determines what we call the amplitude. Amplitude is always positive, and so the absolute value of the amplitude is equal to 1/2 the max minus the min. It's 1/2 that full distance. It's not that full distance. Okay, moving on. What if we have f of x is equal to the sine of b times x? Well, what I like to say is that this makes our graph go faster and faster as b gets bigger. Now b could be smaller too, and in fact I could go down to some fractional numbers, but this would be my normal sine graph. As b gets bigger, how many waves did I have between 0 and 2 pi now? Here's 2 pi right where my pointer is. Now I have 2 waves. Oh, b is equal to 2. How many waves am I going to have between 0 and 2 pi now? I hope that you can see that there's 3 waves. And so b being 3, this is working on the angle measurement here, b times x, so it makes our angle measurement go a lot faster than it usually does. And so we're going to get 3 times as many waves where we used to have it. And then here's 4. So I got 1, 2, 3, 4. It's going 4 times as fast. So here is 2 pi again. And then we'll have 5 waves, 6 waves, and so on. And so we just go faster and faster and faster. Now what happens if b is a fraction of 1? If that happens, then, well, what do you think will happen? For instance, if I go to a half, how many waves do I have where I normally had a full wave? Well, this is 2 pi right here, where the pointer is. How much of a wave do I actually have now? Well, the amount of the wave that you have now is 1/2 of what you usually used to have. And so if we have a fractional amount, a fraction of 1, what's going to happen is it's actually going to slow the wave down. So the period becomes much longer. And so, for instance, if I even go down further, this is 1/5 as much. You can't even see what happens, but what is happening is that this wave is going 1/5 as fast. And so if we start talking about the period is how long does it take the wave to repeat itself. And so if I just am up here at 1, well, one complete period starts here and finishes here. That would be 2 pi. And so the waves just go faster and faster, slower and slower, depending upon this b, and so it will change the period. So if we look at a summary of this, y equals sine of bx, b determines the period. And so if b is a bigger number, that means I'm going to go faster, so I'm going to be dividing by that b. And if b is a smaller number, I'm going to end up actually multiplying. So if b is 0.5, I'm going to be multiplying by 2, and so the period gets stretched out. Also, there's another formula that you could use. You could just switch the b and the period around, and you get b is equal to 2 pi divided by the period. You'll need both of these formulas when we're working with all these trig sinusoidal functions. And I did call these sinusoidal functions. The cosine graph is also a sinusoidal. It repeats. And so we can actually manipulate the sine graph to look like the cosine graph, and so they both are sinusoidal functions. So moving on now to c. If we have the sine of x minus c, this will deal with our phase shift. So if I slide this over, this is going to be a horizontal shift. We do call it a phase shift just because I can match the curve back up to where it was before. For instance, if I just go up to 3.14, and then this is 2 pi approximately. If I go to 2 pi, I shifted the graph so that it looks like the original. So it's equivalent to the original. And that's more so why we call it a phase shift and not a horizontal shift, but you can think of it as the same thing. So let's see what happens here. If I do have 0, this isn't exactly 0 because of rounding, but we'll roll with it. If I have the sine graph here, if I take values of c that are bigger than 1, I'm sorry, bigger than 0, this is going to move the graph to the right, and that's what's happening. This is what we call the starting point. The starting point's right there. And so we've moved that starting point back and forth. We did the same thing with parabolas, but we used the vertex. With these sine graphs, it's a little bit trickier just because you have to find that corresponding point to where we usually would start when c would be 0 or equivalent to 0 there. Okay? So if I move c and make c negative, what's that going to do to this starting point right here? Well, it's going to move everything left. Okay, so this moves everything right and left for the c value. And so the summary, y equals sine of x minus c. C determines what we call the phase shift. The value of c, which makes the parentheses 0, and I'll get into this a little bit later, but c is the value that makes inside the parentheses 0. Later on, we'll put a coefficient here, and it won't be c anymore. So you can't just say that the phase shift is always c. You'll have to solve this out by setting what's inside the parentheses equal to 0, and that will give you your phase shift. C greater than 0 means a shift right, and C less than 0 means a shift left. So now let's look what happens when we have the sine of x plus d. When this happens, well, I hope you can see that this is just going to shift the graph up and down. So if d is greater than 0, I am just going to shift the graph up. And then if d is less than 0, from here, if d is negative, then I'm going to shift it down, and it's by that exact amount. And so with the d value hanging out there on the sine graph, it's going to shift this thing up and down. I hope that's pretty obvious for you. I think we've played around with this in class. So with sine of x plus d, d determines what we call the vertical shift. D greater than 0 moves the graph up by d, and then d less than 0 moves the graph down by d. I actually put absolute value of d. It all depends how you talk about it. But if it moves it down 4, then it was minus 4 for your d value, negative 4 for your d value. So it all depends how you talk about it, but I think you get the gist there. Okay? And then finally, we end up with putting everything together. So here's my overall equation. A sine of bx minus c plus d. And I can have all of these things going on, but watch what happens. So for instance, A, if I change my A value, it's going to work on the amplitude. If I change my B value, it's going to change how many waves I have in a certain amount of time. So right now I'd be going 2.25 times as fast. So my period would be 2 pi divided by 2.25. And then I can even make the B smaller than 1, which really stretches it out. So there's 0.5. So my wave is going half as fast as it normally would. So the period would be 4 pi rather than 2 pi. And then here's my C value. This will move it left and right. And then here's my D value, which will move it up and down. Okay? So in our equation right here, I wrote it without the nested parentheses. And so each one of these will do something different as we look at it, but well, let's take a look overall. So if I ask you to find any of these things and I give you an equation, the amplitude is the absolute value of A. The period is 2 pi divided by B. C divided by B is the phase shift. This is different than what I said before, but that's because I did not have this leading coefficient inside the parentheses. What we're looking for is what value of x brings us back to the starting point, which would be x equal to 0, so to speak. And so what happens is that we set what's inside the parentheses equal to 0 and solve for x. That gives me my phase shift. And then D is simply your vertical shift up and down. And I can get all these things animated and going. I'll show you one. So if I take this thing and I animate, it moves that, and I'll get them all animated all at once. So I'm changing all these values by moving up and down this scale, and so I got everything going all over the place. Kind of fun, huh? Kind of crazy waves. And so we can manipulate these waves and get them going all over the place. Later on in future videos, what we'll do is we'll give you some models and show you how to write the equation of harmonic motion and different things. And then also, if I give you an equation, you should be able to graph some of these things by hand. Thank you very much. I hope you enjoyed this, and I hope this helps summarize how the trig or sinusoidal formulas work, and with the constants and the factors that we use. Thanks.